All right. So, last lecture, this derivation is a little bit complicated, but nevertheless, I need to be really careful, and especially with the board space that we've got. I sent everyone an email that I forgot to include a term in the variation, so I'm going to go through this. Not all of it again. I'm just going to go through part of it again just to make sure. So if you remember, the cost functional that we were the augmented cost functional was this thing phi minus nu transpose little phi, and then plus I had the integral from t0 to tf of L plus lambda transpose f minus x dot dt. And I was just focusing on this part right here. And the thing that I had done was I was first doing the variation in phi. And if you recall, phi was a function of x of t0, x of tf, and tf. So when you take the variation in phi, and this winds up applying to the other term too, but I'll do it for this one first. I had said, and I don't know why I forgot this, but I just forgot it, that t0 appears in two places. So when you take the variation in phi, what you really have is you've got the variation in phi due to a change in x at t0. You also have a variation in phi due to a change in t0, which causes a change in x at t0 because you're changing t0, and then a variation in phi due to the explicit dependence on t0, and the same thing applies to tf. So when you do this, you get the partial of phi with respect to x at t0 times the variation in x at t0. That term is correct. But then you also get this. Everything that accounts for the variation in t0, you've got the partial of phi with respect to x at t0, and then you've got times x dot at t0 times the variation in t0, and then you get plus the partial of phi with respect to t0 times the variation in t0. So this first term accounts for the fact that x changes at a fixed value of t0. The second term accounts for the fact that when you change t0, you also change the value of x at t0, right? If I move t0, I change that. So that changes by x dot at t0 times the variation in t0. You could think of this as the slope times the time distance that has been subtended from t0 to t0 plus delta t0. That's this part here. And then you've got this third term, which is due to this right here. And then you wind up with another set of terms, which looks exactly the same, but they just get applied at tf. And then you've got the variation in x at tf. And then you've got plus the partial of phi with respect to tf times x dot at tf times the variation in tf. And then you've got plus the partial of phi with respect to tf times the variation in tf. That takes care of all the terms associated with that can affect how this function phi varies. Now, if you look at this, you'll see that I can combine some terms here. So when you rewrite this, you get the variation in phi is equal to the partial of phi with respect to x at t0, and then you've got this whole thing multiplied by the variation in x at t0 plus x dot at t0 times the variation in t0. That takes care of this term and that term. And then give myself more room. Hang on. Let me make this a little smaller, just so that I can put it all in one line. Variation in x at t0 plus x dot t0 times the variation in t0 plus the partial of phi with respect to t0 times the variation in t0. And then you've got plus the partial of phi with respect to x at tf times the variation in x at tf plus x dot at tf times the variation in tf plus the partial of phi with respect to tf times the variation in tf. Okay? Now, if you look at that, you'll see that the term in the square braces, well, each of these terms, this first term, the variation in x at t0 plus x dot at t0 times the variation in t0 is equal to the variation in x0. We derived that when we did the standard calculus of variations. And then the same thing applies for the endpoint. The variation in x at tf plus x dot at tf times the variation in tf is equal to the variation in xf. So if I put those two in here, I get the variation in phi is then equal to, I get the partial of phi with respect to x at t0 times the variation in x0, and then I get plus the partial of phi with respect to t0 times the variation in t0 plus the partial of phi with respect to x at tf times the variation in xf plus the partial of phi with respect to tf times the variation in tf. That was the result that I was meaning to write down on the board last time, and I lost track of that one term, so I didn't get it all written down. So that's the variation in phi. Now you'll see that because this other term over here has the same form, because little phi, which are my boundary conditions, also depend upon the exact same quantities, right? So when we do the variation in nu transpose phi, we get the variation in nu transpose times phi plus nu transpose times the variation in phi. Now the variation in phi, because phi depends on, little phi depends upon the exact same quantities that big phi depends upon, right? Phi, if you remember correctly, this little phi was a function of x of t0, x of tf, and tf. So if you go through the argument that you went through for this the Mayer cost, capital Phi, you go through the same argument with the boundary condition function, you'll see that the variation in phi has to have the exact same form as what we got over here, because we're going to go through the exact same sequence of variations for that function as we did for this function over here. Does that make sense to everybody? Does it not make sense to anybody? Seriously, if it doesn't make any sense, I want to know, okay? Because this is really important, because what you'll find when you actually solve problems is you can't just plug in. So if it doesn't make sense, then tell me that this doesn't make any sense, and then we'll go. I'll go through why. If everyone's clear as to why that this makes sense, then we're fine. Okay. This is the partial of phi with respect to x at t0, and then if I go through the same arguments, I've got the variation in x0 plus the partial of phi with respect to t0 times the variation in t0, and then I've got plus the partial of phi with respect to x at tf times the variation in xf plus the partial of phi with respect to tf times the variation in tf. Now, when you do these variations for vector functions, because remember, little phi is not a scalar function. It's a vector function. You must make sure that your dimensions are consistent. You can't just have, your mathematics can't be in just any order you feel like doing this in, right? And if you recall, the way my conventions were set up when I did this, I said that when you take the Jacobian of a vector function of a vector, you're differentiating along the horizontal, not differentiating along the vector. So what I should get is when I'm mapping a vector of length n into a vector of length, I don't know what I call this, vector of length q or something, then I should get a q by n when I'm all done, right? When I take the derivative of this should be however many elements are in phi by however many elements are in x, right? That's the size of this. So, and then this is a column vector. So this should dimensionally wind up working out. So this is a q by n multiplied by an n by 1, which gives you a q by 1, which is what you're supposed to get here, because this here has to have the same dimension as that does, right? Yes, that makes sense to everybody? So you've got to make sure you get all these things. That's why we use the conventions that we use, because it lends itself to not having to write things with lots of transposes, because otherwise if you use alternate conventions, you wind up having to use transposes all over the place in order to get your dimensions to come out right. So if you look at this, you'll be like, well, dimensionally, does all this make sense as far as this goes here? Well, if the variation in phi is a q by 1, I know that nu is also a q by 1. Its transpose is a 1 by q, so I get a 1 by q times a q by 1, which gives me a 1 by 1, which is what I should get, because I'm taking the variation of a scalar, which should give me a scalar, right? So that all works out too. So does that make sense to everybody? Yes? No? Yes? Okay. So we have these two terms now, or three terms if you include the other one, which basically says that the variation, and now I'm going to think about how to organize this. Okay, here's what I'm going to do. I'm not going to put it on this middle board. Put it on the end board. So what I'm going to do is we're going to take just this part right here, and we're going to do the variation really carefully, and we're going to put it to the side so that we have it. Okay? So I've got the variation in phi minus nu transpose little phi, okay, is equal to. Okay, now we're going to write all this down. Now you can see that I've got terms here, I've got this term, I've got that term over there. So if I write this down, I've got the partial of phi with respect to x at t0 times the variation in x0. But there's another variation in x0 over there. Minus nu transpose the partial of phi with respect to x at t0. This whole thing is multiplied by the variation in x0. So that takes care of all variations in x0. Yes? Everyone okay with that? Okay. And then I've got plus the partial of phi with respect to t0 minus nu transpose the partial of little phi with respect to t0 times the variation in t0. And then I've got plus the partial of phi with respect to x at tf minus nu transpose times the partial of little phi with respect to x at tf times the variation in xf. And then I've got plus the partial of phi with respect to tf minus nu transpose times the partial of little phi with respect to tf. This whole thing times the variation in tf. And then I've got minus the variation in nu transpose phi. Okay? I'm going to leave that on that board. Everyone okay with that? Does that make sense? Did I miss any terms? Or no? Did I count for everything? Because if I didn't count for everything, then we're not going to move on. Okay? So I'm going to double check it. So here is my partial of phi with respect to x at t0. That's there. I've got minus nu transpose times this. That is also there. I've got the partial of phi with respect to t0, and I've got the partial of big phi with respect to t0. That's here, and this is here. This is accounted for. Same thing at the final time, and then I've got the variation in nu transpose. Now, that only accounts for the terms outside of the integral. I now have to account for the terms inside the integral. So the part inside the integral is going to require a different approach from the one that we just used to get the terms outside the integral. So now what I have to do is I have to take the variations in the integral from t0 to tf of L plus lambda transpose f minus x dot dt, which, if you recall, I abbreviated this way, of h minus lambda transpose x dot dt, where I defined the Hamiltonian to be L plus lambda transpose f. I defined that last time. So now, let's do this one. This one's more work. Okay? That one was a lot of work. This one's even more work, all right? Which means I have to look at my crib sheet because I'm going to wind up making a mistake if I don't. All right. Here we go. Ready? So first thing we need to do is you need to realize, again, that both T0 and TF can vary, right? So when I do the variation, I'm going to take variations in the endpoints as well as moving the variation inside the integral and taking the variations of quantities that actually vary inside the integral. What doesn't vary? We should have this clear now. What doesn't vary? Time doesn't vary, right? Because it's a dummy variable of integration in the integral that I've got up there, right? So because it's a dummy variable of integration, I don't take the variation in t. There is no variation in t. But what does vary? T0 varies and TF varies. What the confusing part of this, I'm going to say it again, is that everyone thinks that t0 and tf are values of time. They are not values of time. They are two scalar parameters that represent something that you say are the initial time and the final time. They're not the independent variable because it doesn't make any sense. The independent variable is what it is. It's independent, right? It has nothing to do with anything else. It's independent. It does its own thing. So you don't say, I'm going to evaluate the independent variable at t0 and evaluate it at tf. It is what it is. These parameters provide for me a start time and an end time, but they give me something that says I want to go where my integrand goes from here to there. They're two parameters, right? That's what I'm dealing with. I'm dealing with two scalar parameters. So which do you want to do first? Do you want to do the outer terms or do you want to do the inner terms? Because we first have to do the variations with respect to, we have to do all the variations. But what happens, let's do the outer terms first. So if I vary tf, what do I get? Well, what happens is in this here, I'm going to get the variation in the integral, which is going to give me what? It's going to give me h minus lambda transpose times x dot evaluated at tf times the variation in tf. And then I'm going to get minus h minus lambda transpose x dot evaluated at t0 times the variation in t0. That's what comes out from doing the endpoint variations, right? Because I'm taking the variation and then from Leibniz rule and the fundamental theorem of calculus, the derivative of the integral is equal to the function evaluated at the endpoint. So that's what I get, right? So that gives me the endpoints. Now I've got this. I've got plus the integral from t0 to tf of the variation in h minus lambda transpose x dot dt. All right? So now we're going to do the second part of that variation. So in order to do the second part of the variation, we're just going to do this part right here. Okay? So let's do the variation in h minus lambda transpose times x dot. What's that going to equal? Well, it's going to equal the variation in h minus the variation in lambda transpose x dot, right? Which is going to equal the variation in h minus the variation in lambda transpose x dot, and then plus lambda transpose times the variation in x dot, right? That all makes sense? So what's the variation in h? Well, h is equal to L plus lambda transpose f, right? Which is a function of what? It's a function of x of t, it's a function of u of t, it's a function of lambda of t. You see that? It's a function of all of them, right? So when I take the variation in h, it's going to equal the partial of h with respect to x times the variation in x of t, plus the partial of h with respect to u times the variation in u of t, and plus the partial of h with respect to lambda times the variation in lambda of t. Okay? Does that make sense? This last part over here, I'm not going to deal with right away because there's no way to deal with it immediately. I have to do this in separate terms. So I know that I'm just going to integrate this from t0 to tf because everything in here is a variation of a function. There are no variations of derivatives of functions in here, right? They're all the variations in the actual original functions themselves. But over here, I've got a variation in x dot. So if I do the second term, so you can look at this way. If you go back over here, I'm going to take the integral from t0 to tf of the variation in h dt, which is going to give me all those variations over there integrated from t0 to tf. But the last part over here, I'm going to have minus. Now, if you look, I'm going to have the integral. Well, let's do this right. t0 to tf. I'm going to keep the minus sign inside here. Minus the variation in lambda transpose times x dot minus lambda transpose times the variation in x dot dt. Well, this is equal to the integral from t0 to tf of what? Well, I've got minus the variation in lambda transpose times x dot. And then what have I got? Now, I'm going to integrate this term by parts, which is going to give me minus lambda transpose. I'm going to be careful about this. So when I take the minus sign, I'm going to keep it outside the integral for a second. I got lambda transpose times the variation in x dot. So this is like u dv integrated. So I get uv, which gives me this. And this is evaluated between t0 and tf. And then I've got minus, I gotta be careful, minus the integral from t0 to tf of the variation in lambda transpose times x dot dt. And the square braces apply here. Okay? Does that make sense to everybody? Because the minus sign is on this entire variation. It's not on just the terms outside the integral. It's on everything, right? So if you look at this, you'll see that this thing then simplifies to, or then simplifies, or can be rewritten as the integral from t0 to tf of minus the variation in lambda transpose times x dot. And then I've got minus. Now, if you flip the signs on this, you get lambda transpose at t0, right? Or plus lambda transpose at t0, times the variation in x at t0. And then I've got minus lambda transpose at tf times the variation in x at tf. That takes care of those two terms. Minus the integral from t0 to tf of variation in lambda transpose times x dot dt. Wow, that's a lot to do. Yes? Now, you'll see that, look at this term right here. Now, when you break this down, we can combine, well, let's do it two ways. Let's combine the terms inside the integral first. So terms inside the integral. So what have I got inside the integral? I've got the integral from t0 to tf. Now, if you look, I've got the partial of h with respect to x times the variation in x. Is there a variation in x here? Right. When I integrate this by parts, I've got u dv, which gives me uv minus integral v du. So v is this, and then this is a variation in x, and then this is lambda dot transpose v du. This is u, and this is dv. So when I integrate, I get uv minus the integral of v du, which gives me lambda dot transpose times the variation in x. So let's take the terms involving the variation in x. I get the partial of h with respect to x, and then I've got minus, this is a plus, that's a plus, because I'm putting it through the brackets here, plus lambda transpose, lambda dot transpose, this whole thing times the variation in x. So that gives me the first term. And now the second term is, and the second term gives me the partial of h with respect to u times the variation in u. And the third term gives me plus the partial of h with respect to lambda. And now I go back over here, and you see that there's a variation in lambda, and here I've got a variation in lambda too. I've got times the variation in lambda, and then I've got minus the variation in lambda transpose times x dot. We'll fix this in just a minute with the transpose. So that takes care of this term, takes care of that term, it takes care of this term. It also takes care of this term, and it takes care of that term, which is everything outside the integral. So when you rearrange this, you get this. You'll see that you get the integral from t0 to tf of the partial of h with respect to x plus lambda dot transpose. And this whole thing's times the variation in x. And then you get plus the partial of h with respect to u times the variation in u. And then you get plus. Now, if you look at the terms over here, you'll see that everything in here is a scalar. Partial of h with respect to lambda times variation in lambda is a scalar. But there's a lambda variation in lambda transpose. So I can flip these, and I get the partial of h with respect to lambda, and then I get minus x dot transpose, this whole thing, times the variation in lambda dt. That takes care of all the terms outside the integral. That make sense? Okay, now that's all the terms outside the integral. Now let's look at the terms inside the integral. This term's inside. Terms outside. Now the terms outside the integral are a little bit more complicated because you've got to make sure you get all the signs straight on these. Now if you look here, you'll see I've got a lambda transpose at t0 times a variation in x0, x at t0. And now you've got to combine them with the other things that you've got, which are these two terms over here. So look what happens when you do this. You've got a, let's write these terms down. So I've got lambda transpose at t0 times the variation in x at t0 minus lambda transpose tf times the variation in x at tf. That's these two terms right here. Now I've also got these terms over here, which are these two over here. So I've also got plus h minus lambda transpose. Now if I plug in the value, lambda transpose at tf, let's just abbreviate this. Let's say h at tf minus lambda transpose at tf times x dot at tf. This whole thing is multiplied by the variation in tf. And then I've got minus h at t0 minus lambda transpose at t0 times x dot of t0 times the variation in t0. Yes? Everyone okay with that? Now, if you look here, you'll see that these variations are on t0 and tf, but these variations here are on the variations in x at t0 and x at tf. But you recall that the variation in x at t0 is equal to the variation in x0 minus x dot at t0 times the variation in t0. I wrote that down over there, and I erased it already. And I wrote it down earlier, too. The variation in x at tf is equal to the variation in xf minus x dot at tf times the variation in tf. So if you plug these two in up here, you'll see what you get. You get lambda transpose t0 times the variation in x0 minus x dot at t0 times the variation in t0. But I've got a plus lambda transpose t0 times the variation in x at times x dot at t0. So they're going to wind up canceling each other out. So what do we get? So we've got lambda at t0, lambda transpose at t0 times the variation in x at t0 minus lambda transpose at tf times the variation in x at tf. Those are those two terms over there. And then I've got plus h at tf times the variation in tf. And then I've got minus, hang on, I'm looking too far over. Just give me a second. That's too much parallax. I didn't substitute. Lambda transpose at t0 times the variation in x at t0, which is the variation in x0 minus x dot of t0 times the variation in t0. And then I've got minus lambda transpose at tf times the variation in xf minus x dot at tf times the variation in tf. That takes care of these two substitutions going in up there. And then I've got plus h at tf times the variation in tf. And then I've got minus lambda transpose at tf times x dot at tf times the variation in tf. And then I've got minus h of t0 times the variation in t0. And now, because there are two negative signs there, I get plus lambda transpose at t0 times x dot of t0 times the variation in t0. So if you look here, you'll see that there's a minus lambda transpose tf times minus x dot of tf times the variation in tf. So that becomes a positive sign. So this term winds up canceling with this term right here. Does everyone see that? Yes? And then the other term is lambda transpose t0 minus x dot of t0 times the variation in t0. There's a negative sign on this one, but there's a positive sign on this one. So all these terms wind up canceling. So this winds up going away, this winds up going away, that winds up going away, and that winds up going away. And so this gives you lambda transpose at t0 times the variation in x0, that's this term, minus lambda transpose at tf times the variation in xf. And then you've got plus h at tf times the variation in tf minus h of t0 times the variation in t0. Okay, so now let's look at all of this stuff together. Because right now what we've got is we've got the terms inside the integral. Here are all the terms inside the integral. Here are all the terms that survive outside the integral for just the second part, which is the integration part. And then I've got these terms over here, which I derived for the terms that were already outside the integral when I started the variation, right? So what I'm going to do is I'm now going to start combining all these terms, and we're going to combine them, grouping them based on the different variations. So I'm going to start with the first variation, which is the variation in x0. So the terms involving the variation in x0. Let's write them down. What have I got? I've got the partial of phi with respect to x at t0 minus nu transpose, the partial of little phi, with respect to x at t0. That takes care of these. And now I've got what? I've got plus lambda transpose times, well, that's it, lambda transpose at t0. Terms involving the variation in t0 are what? I've got the partial of phi with respect to t0 minus nu transpose the partial of little phi with respect to t0. And then I've got what? I've got minus h of t0. Now the variation in xf, I've got the partial of phi with respect to x at tf minus nu transpose times the partial of little phi with respect to x at tf. That's that term over there. And then I've got what? Minus lambda transpose at tf. That's this term. And then the variation in tf, I've got the partial of phi with respect to t0 minus nu transpose times the partial of little phi with respect to t0, and then I've got minus h of t0. Okay? So that takes care of those. And then I've got another one in here, which I should include, which is the variation in nu, where I've got a term that basically, if you can rewrite this if you want to. This is really trivial. This is equal to phi transpose times the variation in nu, if you want to include the negative sign. Let's include the negative sign. Okay? So the variation in nu gives me a minus phi transpose. Okay? And then I've got those over there, which I'll deal with in just a second. I'll write those down here. So inside the integral, I've got the term that involves the variation in x of t looks like this. It looks like the partial of h with respect to x plus lambda dot transpose. And then the term that involves the variation in u has the partial of h with respect to u, and the term that involves the variation in lambda has the partial of h with respect to lambda minus x dot transpose. Okay, now what do we do with all these variations? Now you have to be very careful as to how you actually deal with these variations, because you can't just start setting things equal to 0 without understanding what you're setting equal to 0. What it says is, I wrote them out this way on purpose so that you could see something. You know that this term is multiplied by the variation in x0, correct? It's in the variation over there, right? If the first variation, so remember, what do we want? We want the first variation in JA to equal 0. If we want that to equal 0, it means every term in this variation has to go to 0, right? So the first term is this multiplied by that. The second term is this multiplied by this, and so on down the line, right? So what it says is it says either this is 0 or that is 0. It doesn't say that one is necessarily 0. It's a product of two things, right? If the variation is going to vanish, it has to vanish for all possible variations. It's not situational. It has to be true for all possible values that variable can take on. So what we're saying is the conditions that come out are as follows, is that it may be easiest to start with what's inside the integral, because what's inside the integral is clearer. It says that either this is 0 or that is 0. If this is 0, we don't have a very interesting problem on our hands, do we? Because it means I can't vary the trajectory, right? If I can't vary the trajectory, I have no freedom to be able to choose the trajectory, the path that the object is going to take. If it's a vehicle going from point A to point B, I have no freedom to choose that path. That's a meaningless problem, right? So the first necessary condition that comes out of this is that the partial of h with respect to x plus lambda dot transpose has to equal 0. What this says is it says lambda dot has to equal minus the partial of h with respect to x transpose. This is what's classically known as the costate equation. It's also called the adjoint equation. You'll find it. You can look it up in different optimal control books. They refer to it differently. The term adjoint is used a lot in the aerospace industry. The term costate is really the more proper term because it's the complementary state is what it really is. X of t is the state, and lambda of t is the costate. But the term adjoint, everyone uses adjoint in the aerospace industry, so you'll find that that's common, and the books reflect that. So that's the first one. The second one is the condition that allows you to be able to figure out what the optimal control is, which it says dh du has to equal 0. Now, there's a problem with this condition, right? Because if u couldn't vary, we wouldn't have an optimal control problem, right? Because you don't have one value of u that would be possible. So u has to be able to vary. But in order to apply this, there's an assumption that's made. The assumption that's made is, remember at the very first lecture, I talked about basic minima and maxima of functions, and we talked about how you can only set the first derivative equal to 0 to determine the critical points of a function if the minima or maxima lay on the interior of the allowable of the interval, right? Well, the same thing applies here. In any real problem, you don't have an infinite amount of control, right? You have a finite amount of control. So u takes on a value in some allowable set of functions. I can allow the control to vary anywhere in this particular set of functions. But if the value of the control that minimizes the objective functional is the one that occurs on the boundary of that control set, dh du may not necessarily equal 0 at the boundary of the control set. It's only if the optimal control lies interior to the allowable control set that this is true. So this is only if u of t, or u star of t, the optimal control, lies on the interior of the allowable control set. If that's not true, then you can't apply this condition. This is what's called, after you've seen the other form of it, you'll understand why it's called this. This is what's called the weak form of, the strong form of Pontryagin's minimum principle. The weak form is the one that allows you to be able to determine the control at the boundaries. I haven't talked about that yet. So assume right now that the control does lie, the optimal control does lie on the interior of the allowable control set. The last equation that comes out of the terms outside the integral is the one that it looks like it's a new equation. The other ones are actually new conditions. But the one that involves the variation in lambda says that x dot is equal to dh d lambda transpose. Now you say, well, that's a new condition, but it's not actually, because if you look at what is dh d lambda, you look back at the definition of the Hamiltonian, it's L plus lambda transpose F, right? So if I take dh d lambda, what do I get? I get F transpose, right? So if I take this, I get F. Right, so this doesn't give me any new information. It just tells me the state equation has to be satisfied, which I knew had to be satisfied anyway because it was in my original formulation, right? So there's nothing new in that. So that takes care of all the terms inside the integral. These terms right here are the ones that come out from the necessary conditions based on the variations at the endpoints. Now, if you look at these, you'll see that there are a few things to note, which is that I'm going to draw a line here. This is now outside the integral, all right? It may turn out, remember when we did the original calculus of variations formulation, I discussed the fact that the endpoints may be fixed or may be free, right? So it may be the case that the variation in x0 is actually 0. It is possible, right? I could have a fixed endpoint, initial point, right? In fact, oftentimes you do have a fixed initial point. So the variation in x0 may in fact be 0. So the terms outside the integral don't conform to just saying that these quantities necessarily are equal to 0. What they say is, it says that for variation in x0, it says either the variation in x0 is 0, or the following condition is met. Let's put it here. Or the following condition is met, which is if I set that equal to 0, I get lambda transpose of T0 is equal to minus the partial of phi with respect to x at T0 plus nu transpose times the partial of little phi with respect to x at T0. If this variation is equal to 0, this condition does not apply. All right? It's the product of these two things that has to equal 0. So if this is 0, and vice versa, if this is not 0, then this condition does apply. All right? Because otherwise there's no way to guarantee that the variation is going to equal 0. So it's either or. This is something you don't really find in optimal control books because they don't go through the either or part of this. Same thing is true with the other one, which is that, so this is 1. 2, it's either the variation in T0 is 0 or the following condition is met. H of T0 is equal to the partial of phi with respect to T0 minus nu transpose the partial of little phi with respect to T0. So that's the second condition. I don't need this anymore. 3, same thing applies for the variation in x at Tf, which says either variation xf is 0 or the following condition is met, which is if you look at that, you get lambda transpose at Tf is equal to the partial of phi with respect to x at Tf minus nu transpose the partial of little phi with respect to x at Tf. And then 4, it says either the variation in Tf is 0 or, and then we get that last condition over there, which is that h at T0 is equal to equal to the partial of phi with respect to The reason that there's the sign on here is different is because if you look back over here, you'll see that these signs are different. So let me just make sure I did the signs correctly. It's a minus h and t0. So this one was correct. This one has a plus. That's the problem. Okay, so this one, this is a negative sign and a plus sign, and that one was correct. This is a plus sign. Okay, so if you look at those conditions, you'll see that there are conditions imposed also on the Hamiltonian, but the condition on the Hamiltonian at the endpoints only applies if this variation is not 0. If the variation is 0, then that condition on the Hamiltonian doesn't apply. Okay? So the upshot of this is as follows, is that if you look, let's look at this now in just a little bit more detail. Because what comes out of this is this like really kind of imposing structure, which looks so confusing that you just like, wow, there's a lot of stuff going on. But what we call these quantities right here, this term and this term over here, if you look at these conditions. These conditions are boundary conditions on the costate. You see that they both affect the costate at the endpoints. The star conditions are typically referred to as transversality conditions. And what they say is that they're transversal because what they're saying is that the product of this condition right here with this variation is equal to 0. So that means the two things have to annihilate each other. If you take the product of them, they have to give you 0. So we call it a transversality condition because of the fact that the product has to equal 0 at the endpoint, and it's a vector equation, so that's why it's typically referred to as a transversality condition. And you'll see that the transversality conditions actually influence the manner in which you can determine information about the costate at the endpoint. If, for example, the variation in x0 is equal to 0, you get no information about the costate at the initial point because this variation is 0, because it's an either or. So if this variation is 0, so when you're doing a calculus of variations problem and you're doing optimal control calculus of variations problem, if the initial condition is fixed and the initial time is also fixed, you cannot get any costate information out of the initial point. None. Because this variation is going to equal 0. Right? Now remember, this is a variation in x0. It's not the variation in x at t0, right? The variation in x0 is equal to the variation in x at t0 plus x dot at t0 times the variation in t0. So if either t0 varies or x at t0 varies, this is not going to wind up being 0. Either way, in either case, it's going to be non-zero, in which case this thing has to be true, right? So you get a condition on a costate only if the respective variation in the state at that endpoint is absolutely 0, is fixed. Similarly at the endpoint. What makes these problems difficult is that you'll see that you will have the following boundary conditions. I'm going to focus on the boundary conditions for right now, because the boundary conditions wind up making all the difference in the world. The first set of boundary conditions is that phi has to equal 0. That one comes out because that's part of the original problem statement. The second one says the two conditions labeled with star must hold if the respective variation in x at that endpoint is 0. So you can see that if part of the state actually is free and part of the state is not free, then you're going to get boundary conditions at both ends in these problems. You're going to have some of the boundary conditions specified at one end and some of the boundary conditions specified at the other end. But in no case, unless you're very lucky, will you get a full set of boundary conditions at either end. You're going to get some at one end, some at the other. So when you're integrating the dynamics, now let's look at the dynamics of the problem. So the dynamics of these optimality conditions looks like this. And I'll finish with this and then we'll we'll go on next time. We've got x dot equals f of x, u, and t, and we've got lambda dot is equal to minus dh dx transpose. This is equal to dh d lambda transpose, just for completeness. So you'll see that this is the system of differential equations that has to be satisfied along an extremal trajectory. So I have to integrate this system of equations. Notice that x is an n-dimensional vector. Lambda is also an n-dimensional vector. So this is a 2 n-dimensional system. That 2 n-dimensional system doesn't have a complete set of initial conditions or a complete set of terminal conditions. So I'm missing information at both ends. So in order to be able to do this, I have to have some method that allows me to be able to figure out what these missing boundary conditions are. In a general optimal control problem, you can't figure out what the boundary conditions are. You have to do it by some kind of numerical method. But what I'm going to go through next time is we're going to do some simple examples of some classical optimal control problems for which you can actually determine boundary conditions at one end by going through some other mathematical gymnastics, and we'll talk about that. We'll talk about it next lecture. Okay?